Welcome to another exercise on the simplex algorithm. As exercise, we have relatively simply here, by using the simplex algorithm, calculate the optimal solution to the following linear problem. Our problem is then a maximization problem with two decision variables, x1 and x2. In addition to this objective function, we also have three constraints, which are 8x1 plus 6x2 smaller or equal to 98, 6x1 plus 8x2 smaller or equal to 98, and x1 plus x2 larger or equal to 14. And finally, we have our non-negativity constraints that x1 and x2 should be larger or equal to 0. Well, to solve this problem, we first have to put this into a working table. And that's what I'm going to do in the next slide. So we take this problem, then we build a table in the following way. Since I have two decision variables, I have two columns, x1, x2 column. I make one row for the objective function and one row per constraint. So three constraints. I add three new variables in each of the three rows for the constraints. To get my coefficients and right side values in the table, I'm going to start with the objective function. Here I have a maximization problem, so I'm going to take the coefficients from the objective function, but I'm going to switch the sign, so I'm going to multiply all of this with -1. So instead of 10 and 12, I have -10 and -12. Then, well, the start solutions here are x1, x2. They're in the basis, so they have a value of 0. So I'm going to insert 0 for x1 and x2, giving me a value of 0 for this function here. For the constraints, I first have to make sure that they're all in the form like the first two as smaller or equal to constraints. Well, here it's the case. So only the last one, the third one, needs to be changed. So to switch from larger or equal to smaller or equal to. How do I achieve this? Well, I can simply multiply the whole equation with -1. Then this sign will change, but all the coefficients will also become negative and the right side value will become negative. So coefficients for x1 would then be 8, 6, -1, these values, and coefficients for x2 would be 6, 8, -1. So those ones. On the right hand side, I will get 98, 98 minus 14. Well, this is already the finished or the first table, but the starting solution is not yet feasible. Why? Because for feasibility, all these values on the right side would need to be 0 or positive. Well, the first two are, but the -14 is not. So how do I make this feasible? Well, I'm going to select the one row where it's negative. If there are more than one, then I would select the one with the largest value on the right hand side. I select this one as pivot row. And to select pivot column, all the negative values qualify. Then I'm going to take a look, is there something positive up here? Well, in this case it's not. So I'm going to select as pivot column where this value divided by this value is as large as possible. So here I have 10, 12, so I'm going to go with x2 as pivot column. So pivot column, pivot row gives me this -1 as pivot element. And with this pivot element, I'm going to go with my simplex transformation. For this, first I'm going to exchange the variables in pivot row and column. So those two, x2 gets here, x5 gets here. For the pivot element, I'm going to divide 1 by pivot element, giving me this. In pivot row, I'm going to simply divide by the pivot element. So this by -1, this by -1 gives this. For the pivot column, for the other values in the pivot column, I'm going to divide them by minus the pivot element, so by 1. So they stay more or less the same. For all other values, I'm going to use a rectangle scheme, meaning, for example, if I want to change this 98, I'm going to take this as one corner of a rectangle and the pivot element as the opposing corner. So this rectangle would look like this. And for the recalculation of this value, I take this value minus these two corners divided by pivot element. Well, so this minus this times this divided by this. If I do it, I will get here to minus 14. Here, for this value, this would be my rectangle. So 98 minus 6 times minus 14 divided by minus 1. For this value up here, I have this rectangle, 0 minus minus 12 times minus 14 divided by minus 1. And this way, I'm going to proceed through all the other values. So I'm going to do this as well for those three, with this rectangle for minus 10, this rectangle for 8, and this rectangle for 6. If I now take a look at my new table, it's still not feasible, so I still have to do some work here. In particular, since here there is a negative value, I have to select this row as new pivot row. And then, well, I only can consider those values which are negative, so only this minus 2 qualifies as pivot element. So this is my new pivot element, and with this I'm going to do my new simplex recalculation. So I'm copying this to the next slide. This is my new pivot element. So with the recalculation, first I'm going to switch variables in pivot row and column. For the pivot element, I'm going with 1 divided by pivot element. In the pivot row, I'm just going to divide all of these two values by the pivot element, so by minus 2, giving me these two. And for everything in the pivot column, I'm going to divide by minus pivot element, so by 2, giving me these values and that. And well, this still leaves those 4 and those 2. So here again, I'm going to use my rectangle form. So let's start with the 7 with the 14. Here I have this rectangle. So 14 minus 14 times 1 divided by minus 2 gives 7. Up here for this 14, I have this rectangle. So 14 minus 2 times minus 14 divided by minus 2 gives 0. Up here, 168 minus 2 times minus 14 divided by minus 2 reduces this to 154. And the same thing is done here for the 12 with this rectangle, for the 6 with this rectangle, and down here with the minus 1 for this rectangle, giving me this new table. Now I see that on the right hand side I only have positive values or 0. So this solution is finally feasible, and I can start with the normal simplex. For the normal simplex, I'm going to select one column where in the objective function row I have a negative value. Well, this already is positive, so only this column qualifies. So this becomes my pivot column. And for pivot element, I'm going to consider all positive values, so 14 and 3. I'm going to then decide on this by dividing right side by the element and select this row where this result is the smallest. Well, here I divide 0 by 14. That's the smallest possible outcome, so 14 becomes the new pivot element. So I'm going to do again a retransformation with 14 as pivot element. So as I said, recalculation with 14 as pivot element. First I switch these two variables in pivot row and column. For the pivot element, I'm going to divide 1 by the pivot element, and everything in pivot row is divided by the pivot element. So 1/14, 0. Everything in pivot column is divided by minus the pivot element. So by minus 14, giving me here these values. And finally, I can do this rectangular scheme, but I have one big advantage here. Since I have a 0 in the pivot row, the respective column will remain as is. So here with this 0 in pivot row, this column remains as it was before, because one corner would be 0 and the results would not change. So this means I start with the recalculation of the other values. I start with this 1, giving me this rectangle. So 1 minus 4 times 1 divided by 14. Minus gives plus. So 1 plus 4 14ths or 2 7ths gives me 9 7ths. Well, this is a positive value. This is also positive. So I know I have arrived at my optimal solution, and I do not have to calculate these two values here because I no longer need them. So I'm at my optimal solution, meaning the values or the variables up here have a value of 0. The variables here have the values from the right-hand side. So x1 is 7, x2 is 7. And together they will result in an objective function value of 154. And well, that's about it on this exercise. So I hope you enjoyed it. I say goodbye and see you next time.